Hello students, in this video I would like to talk about one very interesting application of differential equation. Now before I go into that application, I would like to remind you that we have seen two types of differential equation in this course, namely the first order linear differential equation and a separable differential equation. We have designed the general method to solve both type of differential equations. As I said, differential equation has many applications in the real world. Today we are going to discuss one of the application of this concept. So let's try to start this discussion with something that you guys have seen, many of you have seen in your basic algebra course, or even in high school you have seen formula to calculate this term. So let's start our discussion by understanding what is so-called continuous compounding. Right, I am going to write down one very interesting statement about continuous compounding. In the past, you were given a formula. Using that formula, you were calculating continuous compounding interest or amount after a certain time period. Let's try to understand the source of that formula. All right. So here is the statement. An amount of, let's say, $1 invested at an annual interest rate R% grows according to this formula. dA by dt equal to rate of interest times A. Right? So amount in the bank account grows according to this differential equation, according to the solution of this differential equation. Now think about it for a second, that why this solution is important for us. If we know the solution of this differential equation, we can compute what is the amount in the account after 10 years, after 15 years, after 20 years, and so on and so forth. Right? So many interesting type of problems can be answered with the solution of this differential equation. For example, how long person needs to wait till his account hits certain figure. Right? So these are the type of problems that one can address using the solution of this differential equation. I would like to mention one remark here. This is a very special type of differential equation. Right? Above differential equation is separable. I can see variable A separate from variable T. Remember, R is a constant. Interest rate is not going to change. Alright? It's a separable DE as well as first order linear DE. So this is the differential equation that falls in both category. You can solve this differential equation using any method you like. However, it is recommended that you use the first order linear differential equation method to solve it. I'll tell you the reason why I want you to use that particular method. Alright? But for now, let's try to keep it simple. We have result differential equation involving continuous compounding. I would like to give you two more results here. So this was the first result. Result number 2 is slightly modified version of continuous compounding. I'm going to call it continuous deposit. Right? So suppose we have this situation, an amount of $1 invested at interest rate of R% compounded continuously. If an amount of $D invested every year then the amount in the account grows according to the following differential equation. You have dA by dt equal to rate of interest times A, and then remember, the person intends to make a continuous constant deposit of $D every year. Alright, so every year $D will be added to this initial amount. Alright, so this modified differential equation refers to modified situation. Very trivial example would be this, that suppose somebody wants to save some money for his or her retirement in coming 25 years, right? That person deposits, let's say, $15,000 in some IRA account or some bank account, and he would like to make $1,000 investment every year, and he would like to know that after this 25 years, at the time of his retirement, what is the amount he's gonna get. Right? So in order to address that issue, in order to answer that question, you will have to solve the second differential equation. Remember, the only thing that is different from the first situation is that initial deposit is there with certain interest rate, but then continuous deposit of $D is being made. Let's think about slightly more interesting case, very similar to number 2. Suppose instead of making continuous deposit, let's say somebody make continuous withdrawal, right? How do we write modified differential equation? Fairly easy, no? Instead of plus D, you would do minus D. A very typical example is like, let's say somebody wins a lottery of $1 million, right? That person deposits this $1 million in some bank account which pays interest rate of, let's say, 3% on a yearly basis. This person intends to make continuous withdrawal every year of $10,000 from this account. He would like to know that what will be in his bank account after 10 years, after 20 years, right? So this type of examples are called continuous withdrawal example. We can write down the statement in a very similar language. Let's try to write it down, okay? So here is the third part 3 of the result. It's about continuous withdrawal. We are going to write down this statement in the same way. An amount of $1 invested at interest rate of R% compounded continuously. If an amount of D dollars are withdrawal is withdraw from withdraw every year, then the amount in the account decays. Alright, so it's going to decrease according to this differential equation. dA by dt equal to rate of interest times A minus continuous withdrawal. Alright, so as you see, we have this three interesting part of the same result. Continuous compounding is something that you guys have seen already in the past. Continuous deposit is a modified version of the same differential equation to make the situation slightly more realistic. Alright, and continuous withdrawal sits in the same boat. Right, it's a more realistic situation.